Section 8.3, straight from the book. We're going to be graphing reciprocal functions. The previous video was just an intro where we actually graphed this function right here. But instead of f of x, we wrote it as y equals 1 over x. And we made an xy table and we plugged in values, pulled out answers, and we noticed that it was a curve like this and it had an asymptote. So this was infinitely approaching the x-axis, and this way it was infinitely approaching the y-axis. And likewise over here, infinitely approaching the x-axis, the y value of 0, and going this way, infinitely approaching the y-axis, the x value of 0. So we did that yesterday. We also recognized that the value of 0 would make it undefined for x, which makes total sense. The x-axis at the value of 0, the graph never touches it. There is no value. So the first thing that the book asks you to do is to understand which values would make it undefined. So right here, the value of -2 would make this whole function undefined. Right here, the value of 5 would make this whole g of x function undefined. Over here, the x value of 0, 3 divided by 0 is undefined. So the first thing I want you to do is to identify those values that'll make it undefined. And why is that? Because those values ultimately become the vertical asymptotes of these graphs that are called hyperbolas. I mentioned that in the previous video. This type of graph is called a hyperbola. It's kind of like where you have two curves that are mirror images from each other. We'll get into this in a couple of minutes. But right now we want to focus in on finding that value that would make this f of x function undefined. So in the book they explain, well, if you're trying to find the value that'll make it undefined, you're really trying to find the value that 2x plus 5 will be 0 at. So they actually set up the 2x plus 5 to equal 0, and then they solve it, and it'll tell you x equals -5/2. I sometimes like to write it as it cannot equal 0. So I sometimes look at this guy and I say, okay, 2x plus 5 cannot equal 0. And then I solve it like I normally would, right? -5 minus 5. 2x cannot be -5. Divide by 2, divide by 2. Answer is x cannot be -5/2. What does that mean? That means that the asymptote is at x equals -5/2. Okay. The reason why I sometimes, like they wrote it with the equal sign, okay? The reason why I sometimes write it with the not equal is because if you ever want to state the domain, right, you're talking about the x values going to the left and going to the right, then you're going to say that the domain is all real numbers, but x cannot be this -5/2. So it's up to you. Just remember that the value -5/2 will make it undefined. And what would that mean visually on a graph? Well, if you went to your xy plane and you went to -1, -2, -3, -5/2 is really -2.5, which would be right here. And x equaling -5/2, that would produce a vertical line. So this is technically your vertical asymptote, okay? So if you were to identify that your horizontal asymptote was let's say the x-axis itself, then you could easily be able to identify your graph that would probably be like this and like that. Okay, anyway, I know that's a little too much for right now. Again, this first page of the book is just worrying about, or it's just emphasizing for you guys to be able to identify the value that'll make it undefined. Let's move on to the next page. So what they want you to do here in the book is to learn how to identify the asymptotes and also identify the domain and range of each function. So they don't want you to graph yet, but they give you the function f of x equals 2 over x minus 3, and they want you to visually identify the asymptotes. And then after you identify the asymptotes, state the domain and range of each of these functions. So some of us might think, well, oh, these are two different functions. No, it's the same function. This is what we call a hyperbola. Both of these curves come from this f of x, this single f of x function. Okay. So where are the asymptotes at? The question that I'm really asking is, where do these graphs infinitely approach but never actually touch? So you could do it algebraically to find the vertical asymptote. Well, algebraically, what would that mean? You can't let the denominator become 0. So you don't want this to be a 3, right? I mean, you could actually show your work. You could say, okay, x minus 3. If you set it equal to 0, you're going to find your vertical asymptote. Plus 3x equals 3. That means that at the x value, remember this is the x-axis, at the x value of 3, 1, 2, 3, you have a vertical line, which is your vertical asymptote. And we didn't even have to actually do that math. I mean, you could clearly see that it's approaching this line and that this one's approaching that same line, that value of x equals 3. So that's your vertical asymptote. How about visually? What kind of horizontal asymptote does this have? Well, yeah, we said this way it approaches this x value of 3. This way, what? It doesn't approach an x value, it approaches a y value. What y value does it approach? And likewise, this way, what same y value does it approach? It approaches that y value of 0, which is the x-axis itself. Okay, so let's really understand this. The vertical asymptote was found by setting this equal to 0. So that vertical asymptote is x equals 3. The horizontal asymptote, the asymptote that runs left to right, that's actually the line y equals 0, the x-axis, but which is the line y equals 0. So let's try another one. This one down here, they give you a function. Look, they get pretty interesting, huh? You got a fraction, you have something down there with the x, which yesterday we were supposed to conclude that this produced a horizontal shift, this produced a vertical shift. We'll talk about that in a minute. Right now we just want to identify asymptotes. So you could identify your vertical asymptote just visually by saying, okay, -1, -2. Yeah, it looks like both of these graphs is approaching the x value of -2, and it's approaching the x value of -2. So this is my vertical asymptote, which is x being -2. That's my vertical line, x equals -2. Now you could have also done that algebraically. You could have said, okay, this cannot be 0. If my x plus 2 was equal to 0, the whole thing would become undefined. So if you solve it, x equals -2. So that's how we get this vertical asymptote, x equals -2. Now how about that horizontal asymptote? From left to right, this approaches a certain y value. It's not the x-axis anymore. It's not the y equals 0 anymore. It's actually approaching the y equals -1, right? This is the -1. And likewise, this one's also approaching that y equals -1. So that horizontal asymptote is right here. Okay? And that would be the horizontal asymptote y equals -1. So, we're supposed to, I mean, we saw that visually, but algebraically, you're supposed to see that that -1 is actually giving you that horizontal asymptote. So yeah, the vertical asymptote comes from the denominator. The horizontal asymptote comes from the constant that's being added or subtracted at the very end. So I guess I haven't been going through everything that the book wants us to go through. Let's go back up here because I did state the vertical asymptote, x equals 3, and the horizontal asymptote, y equals 0. That's what they wanted us to do, identify the asymptotes. But then after that, they wanted us to state the domain and the range of each function. So let's state the domain. You're going to put D. And what about the domain? What about the x values? Do these graphs go to the left forever? Yes, it does. Does it go to the right forever? Well, not this one exactly, but this one does. So the x values really do exist everywhere on this side and everywhere on that side, except for that single value of x equals 3, which will make the whole thing undefined. So what are we saying? The x values of this hyperbola are all real numbers. but x cannot be 3. Okay, that's one way of writing it. They actually write it that, let's say, looking down here, they say that the domain is all real numbers not equal to 3. All right, so instead of saying but x cannot equal to 3, they actually write it out in words not equal to 3. So it could be any number you want, but x cannot be equal to 3. I prefer this notation. It's up to you. And the range, what about the range of this guy up here? Well, does it go up forever? Yes, it does. Does it go down forever? Yes, it does. So when we're talking about range, you're going to say that y is also all real numbers, but you also want to say that but y cannot be what? Y cannot be 0. Okay. Remember, here's your asymptote, your horizontal asymptote, y equals 0. It's not at y equals 1. It's not at y equals -3. It's at y equals 0. Okay, so you have to say for the range, but y cannot equal 0. Okay, so that's how you state the domain and range. So that's the main point of today's lesson, to be able to look at a graph, identify the asymptote, the vertical asymptote, the horizontal asymptote, and also to be able to state the domain and range, which is pretty much all real numbers, but those asymptote values. So this one down here, we stated the vertical asymptote was x equals -2. The horizontal asymptote was y equals -1. And to state the domain of the hyperbola, you're going to say x equals all real numbers, but x cannot equal that vertical asymptote -2. And the range is y equals all real numbers, but y cannot equal that horizontal asymptote, y equals -1. Okay, y cannot equal -1. So once again, we're supposed to identify these asymptotes and start recognizing something, that the vertical asymptote is going to be found with this denominator by setting it equal to 0 and finding the value that would mess it up, that would make it undefined. That'll give you the vertical asymptote. And the horizontal asymptote comes from this constant value at the very end. Now that should ring some bells. You should feel familiar with this, like if you've already done this before, because in a way you kind of have. Here's the next page, and here's the key concept. The key concept, all right? It's another form that's good to have memorized, right? F of x equals a over x minus h plus k. I know you guys are thinking, hk, wait a minute, I know h and k. Absolutely, you guys already know h and k, and you even know a. Let's go back to something that we're really familiar with. Let's say the vertex form parabola. Vertex form parabola. And that's y equals a parentheses x minus h close parentheses squared plus k. We should remember that the h value is always with x, and you always have to think opposite of whatever value you see here. And that does ultimately produce a shift on the x-axis, right? From the parent graph coming to this new graph, the h produces a shift on the x-axis. The k is the constant, the value that's all by itself at the very end being added or subtracted, and that produces a shift either up or down, right? And the a value, that determines if your parabola is getting vertically stretched or compressed. And also, if you had a negative sign out here, it would reflect it over the x-axis. I hope we remember all that stuff. So let's take a look at, let's go back to that first example that we did. This was it. This is from the other page. As a matter of fact, let's go back and show the actual one that we did on the other video. Here it is. I just copied and pasted it. So we actually did all the work right here for this original equation, y equals 1 over x. And we had the horizontal asymptote, the vertical asymptote, and we plugged in inputs and outputs, and we got these graphs right here. Awesome. Now, what would happen back in a parabola, back with the U-shaped curve, what would happen if the a value would change to a negative? Well, if the a value would change to a negative, your parabola would no longer open up. It would actually get reflected on the x-axis and open down, right? So what would happen if I put a negative for my a value? If I put a negative in front of this thing? Well, the graph would no longer be right here and right here. It would get reflected over this x-axis. So if I put a negative right here, it would actually switch it to be over here, and down here. It would reflect it over the x-axis. I hope that kind of makes sense. I don't want to confuse anybody. But the a value, if you change it to a negative, it does cause a reflection, okay? Now, what if my a value got increased? Like if I changed the a value of this red parabola, if I changed it to a 2, it would get narrower. If I changed it to a 3, even more narrow, it would get more stretched out. So the a value causes a vertical stretch or a vertical compression. It either makes the parabola wider or narrower. So right here, if I change my a value to like a 4 or a 5 or a 6, something bigger, now you're thinking, well, where's the a value? I know that my a value is out here in front of the parenthesis. Where's my a value here? Well, let's go back to the book itself. The a value, it's still the number that's out in front, but if you think about a fraction that's being multiplied by a number that's out in front, you could just put that number up on top, right? If I say, what's 1/2 times 2? Well, you could put the 2 on top and it'll be 2 over 2, which is 1. So if you ever have an a value times a fraction, you might as well put that a value up on top. So that's why the a value is up on top instead of out here in the front. Anyhow, the a value will cause a vertical stretch or a compression. It'll make it either, if it were a parabola, narrower, if it were a stretch, or wider if it were a compression. Right here on this guy, it would just make this, like this dot would be higher up. This would be higher up. So it would make it like stretched or compressed. It could make it like maybe this one further down. So it'd be more compressed closer to that axis. Anyhow, the a value is a stretch or a compression. If it were a negative, it causes a reflection over the x-axis. And again, the h value is always with x, and you always think opposite of what you see, and that will give you your vertical asymptote. The k value, you always take it for what it is, and that'll give you the horizontal asymptote. And everything becomes easy once you understand that. So for example, right here, I could easily identify my asymptotes. What's my asymptote? My asymptote will be x equals +4. Why +4? Because you have to think opposite of what you see here. And how about my other asymptote, my horizontal asymptote? That'll be y equals 2. Remember, the h, you think opposite. That's why we have +4. And the k value of 2, you take it for what it is. That's why it's just y equals 2. Now, just by knowing that, guys, just by knowing that, you could actually go to an xy plane. That's a disgusting xy plane, I apologize. But imagine this. Go to the x value of 4. Go to the x value of 4, 1, 2, 3, 4. That will be your vertical asymptote, okay? And let's go now to the y value of 2, 1, 2. And this will be your horizontal asymptote, okay? So once you know your asymptotes, let me ask you this. Is your a value positive or negative, right? The a value is 2, which causes a vertical stretch, but it's positive. It's not negative. That means it doesn't get reflected over the x-axis. That means that it's going to look like this parent graph that we started with. Sorry about that. Here's the original parent graph that we started with. It's down here and up here. Since the a value is still positive, it's still going to be down here and up here. If it's negative, that's when it gets reflected to this other side. But since it's positive, it's still going to be down here and up here. So we could draw it from those asymptotes. Just draw it down here and up here. And guess what? We have our graph. A good sketch of it, at least. I mean, we don't even have graph paper, but check it out. I mean, if we actually look at what they graphed over here, that's it. It's right there. Same exact graph without graph paper, without a graphing calculator, just by identifying the asymptotes, okay? The vertical asymptote will be by setting this one equal to 0, or you could just think opposite of what you see here, okay? And the k value is the number that's out here by itself, right? So the vertical asymptote, x equals +4, the horizontal asymptote, y equals +2. It's that easy, guys. So let's actually get into what the book is explaining right here. Let me actually delete this. All right, so it says right here, they want you to graph each function, and we already did a sketch of it. That was quick, it was easy because we identify h and k. But let's go through and see how they are explaining that this graph comes from the parent graph of that first one that we did, y equals 1 over x, okay? So the a value is 2, right? That a value is 2. So what does that really mean if you want to describe how it changes from the parent graph? This was the parent graph that we did on the other video, right? How does it change from this parent graph to this new graph that we have up here, or this one that's nicer that they did for us? How does it change? Well, the a value of 2, that causes a vertical stretch, all right? So it gets vertically stretched by 2, okay? What else? The h value of 4, that means that it gets, they use the word translated, but ultimately that means shifted, right? It gets shifted 4 units to the right. So you think opposite of what you see here. So it gets shifted 4 units to the right. So let's take a look at this original vertical asymptote. It gets shifted 1, 2, 3, 4. That's why it's over here now. As you can see, it gets shifted 4 units to the right. And then the k value of 2, that means it's going to be a shift of 2 up. So these shifts of h and k, that's what I wanted you to conclude, to discover on your own with the previous video, right? But if you didn't get it, I hope you get it now. The h and the k, like always, are your shifts. The h is always with x. You think opposite of what you see, and that'll tell you how to shift either left or right. The k value is always being added or subtracted at the very end, and that'll be the shift up or down, depending on if it's positive or negative. So how about this? Let's zoom in on this a little. Let me actually cover this up. That didn't work. Let me try that one more time. Here we go. Now let's walk through this. So from the original parent graph, from the original one that looks like this, right, this guy right here, what happens? What characteristics change? What are the transformations to get to this new f of x function? Well, let's begin with the a value. It is a negative 3. So this negative means that it gets reflected. So if I'm looking at this guy, this negative sign is going to cause an immediate reflection. That's the first type of transformation. So instead of this guy being down here, it's going to get reflected over the x-axis. So a mirror image of that guy down there is going to, on the x-axis, is going to be up here. And likewise, a mirror image of this guy over the x-axis is going to be down here, right? So let's do that. So this is what that's the first transformation that happens. In addition to that, the 3 causes a vertical stretch. So it's going to make this stretch further this way. So it's going to be a little more kind of like this, right? Same thing over here. Okay. And I know it's getting ugly because I'm drawing everything on top of each other. But then in addition to that, these green graphs, this green graph right here, it's going to get shifted 1 unit to the left and 4 units down. So this guy's going to go 1 unit to the left and 4 units down. Same thing with this guy. And if you think about that and you start looking at the actual end graph here, that's exactly what happens. There was a vertical shift down 4 units, and it got shifted 1 unit to the left. So those are my asymptotes, really easy to graph. Let's say they want you to state the domain and range of these guys. Again, we know that these hyperbolas go to the left, to the right forever, go up and down forever, but they can't be those values that are called the asymptote values, right? So when you look at the domain that they give down here, the domain, they don't say x equals all real numbers. That's what I would say. They just say x cannot be -1. Obviously, x cannot be -1 because that's the only place that there is no x value. So you could state it this way. I like to stick with our notation of saying, yeah, for the domain, x could be all real numbers, but x cannot be -1. Same thing for the y. For the range, the y values, y could be all real numbers, but y cannot be this -4 value. Okay, that's what they say here. The range, y cannot be -4. So, just to one final practice. What happens from the original parent graph to this one? You would first say it gets reflected over the x-axis because the a value is negative. After that, you would say then it gets vertically stretched by a factor of 2. After that, you would say it now gets transformed. It gets shifted. I'm sorry, not transformed, because the whole thing's a transformation. It gets shifted 4 units to the left, because you think opposite of what you see here, and 1 unit up. Okay. Now, if I wanted to do a quick sketch of this, oh man, it's so easy, right? So easy. Identify your asymptotes. Well, your vertical asymptote will be at the x value of -4. Here's your vertical asymptote. And your horizontal asymptote will be at the y value of 1. Okay. And this did get reflected over the x-axis, okay? So the original one was down here and up here, which means down here and up here like this. If it got reflected over this x-axis, it's no longer like this. It's now gonna flip this way, and it's gonna be like this. Sorry. So my graph will be up here and down here. And there's my graph. I mean, if they tell you to graph this, it's really easy. Whoa, that kind of went off. Check out their graph. Well, actually, well, they don't have their graph, but it's really that easy, guys. All right? Sorry about the long video. Let's keep the assignment simple, huh? How about this? All you need to do is identify the asymptotes, the domain and range of each function, and that's it. So let's go through. If you're at home, hit pause. That way you could have these problems. Let's do the asymptotes. So I'll do one of these 4. You guys do the other 3. I'll pick, I want to go with number 10. So they give you the graph. They want you to just identify the asymptote. Okay, so the vertical asymptote looks like it is right here. Okay, and you could even algebraically see that vertical asymptote being the x value of 1, because 1 minus 1 would be 0, would make it undefined. So this one's slightly confusing because it doesn't go 1, 2, 3, 4. It's actually going 2, 4, 6, 8. So when you think about the x value of 1, that's really right here. It looks like it's halfway between. That's because it's halfway between 0 and 2. So 1 is right here. So that's the vertical asymptote. So what would we say for number 10? The vertical asymptote is x equals 1. How about the horizontal asymptote? Well, the horizontal asymptote's right here. Visually, you could see that it's perfectly between the value of 4 and 6. The value perfectly between 4 and 6 is 5. So the horizontal asymptote will be the y value of 5. And of course, you could clearly get those vertical asymptotes from your h value and your horizontal asymptote from your k value. So what else do they ask us to do here? State the domain and range. Okay, simple. The domain will be x equals all real numbers, but x cannot be that vertical asymptote value of 1. Okay, and the range, same thing. Y could be all real numbers, but y cannot be that horizontal asymptote of 5. Okay, so that's what we're doing. Again, I want you to do 7, 8, and 9. Just write down, you don't have to copy down the graphs, but you could just write down the information. Number 7, vertical asymptote x equals 1, horizontal asymptote, or actually number 10, vertical asymptote x equals 1, horizontal asymptote y equals 5, domain range. Okay, so do 7, 8, and 9. And let's also do a rough sketch. Right here it says graph each one, state the domain range. Let's do a rough sketch of numbers 11, 12, and 13. How's that? 11, 12, and 13. Here's 11. Hit pause. There's 12. Hit pause. And there's 13. Hit pause. Okay. So you're going to be doing 11, 12, and 13. it's as easy as this. I'll do the example of number 15, all right? So let me actually take this 15 and show you how easy it is to graph it, okay? Identify your vertical asymptote. That's your h value. So what's your h value? H is always with x. Think opposite of what you see here. There is no x plus 1 or x minus 7. It's just x. So what's your h value? It is 0. Okay, so your vertical asymptote is 0. Okay, so where's x equals 0? It's right here. There's your vertical asymptote. Here it is. This is your vertical asymptote. How about the horizontal asymptote? Well, that's your k value. Your k value is actually 3. So you're saying y equals 3. That's your horizontal asymptote. So where's the y value of 3? Well, here's 1, 2, 3. Here's your y value of 3. Okay. And now, is this a value positive or negative? It's positive, which means that the original one that we did, that parent graph that's down here and up here, it's going to stay like that. Okay. The 2 only causes a vertical stretch. So instead of it being pretty close to it, it gets a little further away, it gets stretched, but it's still going to be down here and up here. And there's my graph. That's it. Okay, it's that easy. Okay, it also says state the domain and range. Well, you would say the domain is x equals all real numbers except for 0. The range is y equals all real numbers except for 3, but y cannot be 3. Okay, so it's super easy. Let's have you try again 11, 12, and 13. So your homework is page 549, 7 through 10, and numbers 11 through 13. I wrote 11 through 13 right here. And again, you're just sketching a graph. How? By doing your asymptotes first, according to h and k, and then thinking if it gets reflected or if it doesn't get reflected. All right, guys, I hope you understand. If you need to, watch this video again a second time so you can get it better.